Hello. Hello. Yeah. Can you hear me?
Can you hear me?
Yep. Yep.
Thomas, hi, how you doing?
Oh, so there are also old people attending the talk. So I'm not the only
I
old
just
person listening to
no,
myself.
it's two of us. So I just stopped by to say hi. I'm going back to the audience, on YouTube channel.
Okay. Okay. So what should I
I'm
do
gonna
now?
attend the
Should I share
just you
just
just yeah, share the screen. It's everything as usual, but all the audience is on YouTube channel. We are broadcasting the talk in real time.
okay, okay, okay.
So good to
Oh,
see you again. Looking forward for to your presentation.
yes. Okay. Cheers.
Thank you, Nissan.
Yep. Thank you, Andy.
This is not what I wanted to do. I want to share the window actually. Give me a second, please.
Yes. Please take your time.
I thought this is sharing the window. Oh yeah, now it's okay. So go to presentation mode. Okay, so do you see it okay?
Yes. It's totally fine now.
Okay, so let me know when I can start.
Yep. So first, I'll just give an intro for you, and then we can
Okay.
start the
o-
talk. Okay.
Okay, okay.
Um, yeah, again, thank you for being here and presenting us this wonderful topic. Hello, everyone. Uh, Welcome back to DDLC seminar series organized by the IDS Lab at Cornell University. This is Nishant, and uh, I'm really pleased to give an introduction for Dr. Thomas Parisini. Yeah. Before we begin the talk, Dr. Thomas Parisini is going to talk about control theory for optimization today, and a little bio about Dr. Parisini. Dr. Parisini did his graduate studies at the University of Genoa, Italy, and he was an associate professor with the Politecnico di Milano. And he currently holds the chair of industrial controls and is the head of control and power research groups at Imperial College London. He also holds a distinguished professorship at Aalborg University, Denmark, and he has been the since 2001 he has been the Daniel Endowed Chair of Automation Engineering with the University of Trieste, Italy, and where from 2009 to 2012 he was the deputy director. In 2023, he held a scholar in residence visiting position with Digital Futures KTH, Sweden, and he has authored or co-authored a research monograph in the communication and control series, Springer Nature, and more than 400 research papers in journals, book chapters, and international conference proceedings. Dr. Parisini was the recipient of the Knighthood of Order of Merit at the Italian Republic for scientific achievements, and it was awarded by the Italian President of the Republic in 2023. In 2018, he received the honorary doctorate from the University of Aalborg, Denmark, and in 2024, the IEEE CSS Transition to Practice Award. And moreover, he was awarded in 2007 the IEEE Distinguished Member Award and was co-recipient of the IFAC Best Application Paper Prize of the Journal of Process Control. And he has and he has had a number of contributions when it comes to serving as editor in chiefs in various prestigious journals like the Automatic. He's currently serving as the editor of Automatica and editor in chief of the European Journal of Conference, and he has served in the editorial board of transactions in automatic control and transactions on neural networks. And he also received a 40 million euro grant from in 2016 when he served as the principal investigator with the Imperial of H2020 European Union flagship teaming project. And in 2021 to 2022, he was the president of the IEEE CSS Society, and he was the editor-in-chief of the Transactions on Control Systems Technology, TCST. And he has served on the board of IEEE CSS Control, the conference editorial board. And yes, again, like he has served on multiple journals as editor-in-chief and in the editorial committee. And he's a fellow of IEEE and IFAC, and he's also a member of IEEE TAB Periodicals Review and Advisory Committee. And without further ado, I'll let Dr. Parisini take over the talk.
Thank you so much for this presentation. And yes, I forgot to not to tell all these things because I already feel quite old. And so anyway, okay. So yes. So thank you. So how much time I have? 45 or 50? I don't know. I mean, can you remind me?
It's about 45 minutes, but you can take more time. Like since it's gonna be
okay.
streamed online and saved for later view, so
Okay.
you can take your time to.
Okay. Okay, so the title of the talk is, you can see it here. It's important, first of all, to mention that this work would not have been possible without the leadership by my two younger co-authors, Michelangelo Bin and Ivano Notarnicola. They are both now associate professor at University of Bologna in Italy. So the title of the talk is already, I mean, giving the message, okay? So here we are taking some optimization scenarios, and we try to use, and in some cases we succeed, to use control theory tools and methodologies in order to improve these algorithms, but especially to prove and show that they have properties that were still not discovered, okay? And that is something that we found very exciting and interesting, and I hope it will raise some interest in the audience as well. Okay, so let me then start, okay? Let me give an outline of what we want to do and what we want to actually explain today. So, first of all, the main motivation we have here. So control theory methods are proved to be extremely powerful, okay, in order to design and especially provide an analysis which is effective for algorithms where this analysis is non-ad hoc, okay? The important thing is that. So it's a general approach, okay, where we should not change too much the analysis if we change the algorithm, okay? And that was one of our main goals. And our other main goal is that one important aspect that many times is neglected in the analysis and design of optimization algorithm is not just the convergence, but the robustness properties. And I will try to motivate that shortly. The other important aspect is that we focus on the discrete time case, because most of the analysis scenario that you find in the literature are done in continuous time, but then the algorithms are actually implemented in discrete time by construction. And unfortunately, the analysis tools that work very well and are easy to use in continuous time do not carry over in the discrete time scenario. So that was kind of a little bit of a hole in the literature, in a gap that we tried to fill as much as we could. And notice that in the title of this slide, in the title of this slide, I explicitly enhanced the word distributed, because distributed optimization is clearly getting more and more importance, also due to machine learning applications that are now applied, like, for example, federated learning or learning over wireless network, where really you have to solve an optimization problem by doing local optimization computation by agents that not necessarily share the entire information. What we deal with in this talk are three use cases, basically. Two are dealing with unconstrained problem, okay? We consider the use case number one, which is distributed consensus optimization, a use case number two, which I personally believe is extremely interesting, which is distributed global minimum sharing. And then after we do that, we will deal with the more difficult case, much more difficult case, I have to say, where we add constraints, okay? And then we will deal with the centralized case first, and at the end of the talk, if there is time, I will tell you very recent result that we got in the distributed scenario. Okay, let me start with use case number one, distributed consensus optimization. Okay, so this problem, where actually all these activities started from, actually came from by chance, okay? Casually, I was a colleague of mine here at Imperial. He got a very prestigious grant. He's a person in information theory and communication, and he wanted to implement, okay, an experiment, a collaborative learning among edge devices over wireless network. He is not an expert in optimization, and so he took the more popular algorithm off the shelf, okay, which is basically gradient tracking, okay? Gradient tracking in the distributed optimization is quite a standard algorithm, and he thought, wrongly, unfortunately, but he thought that he could get this algorithm, just plug it into his experimental setup, and use it in order to solve this collaborative learning algorithm that he wanted to implement. Once he did it, the algorithm failed terribly in a way. Okay, here you see some of the results that we got. Okay, and let me explain a little bit about what actually didn't work out here. Okay, so the reason for the failure is that most of the works that deal with distributed consensus optimization and gradient tracking in particular focus on nominal performance only, which means perfect measurements, no uncertainty in the dynamics, and more importantly, perhaps, correct initialization, which means they do not have global convergence, okay? And in fact, in this case, the problem was coming from the fact that the inevitable quantization errors that you have in this kind of application, especially when you implement it on real device, okay, it's not the nice theoretical quantization, which is evenly distributed, zero mean and whatever. No, here you have a truncation on the fifth decimal value of the numbers. Therefore, the computation was biased, and that bias was generating this blowing up of actually the error with respect to the optimum you want to achieve. And surprisingly, the performance were getting even worse, decreasing the descent step, which is a bit counterintuitive also, okay? Why did that happen? I already mentioned it a little bit, but the problem is that this, unstable behavior of gradient tracking is a byproduct of non-global convergence, okay, and the lack of robustness, okay? And therefore we say, okay, this is a typical case where a person doing research in control, I mean, this is what we do every day, right? So to address robustness, to address convergence, to address stability, hopefully global stability, and so on. So we said, okay, let's try to understand what we can do here. And let me then do it and explain it to you. I try to not to be too much going into the technical details, okay? I will try just to explain the basic aspect. Okay, So the problem setup that we are dealing with here is explained in this slide, okay? So basically you want to minimize, okay, a cost function like that, where each agent can only compute the local gradient, which means the gradient of the local cost function. Each agent does not know what the other functions are, and you want to minimize over the entire network the summation of this function, okay? As far as communication is concerned, the communication is limited only with neighbors, okay? So each agent can only get information from their neighbors in the assumption that you have a connected undirected graph, okay? And the algorithm, the gradient algorithm tracking algorithm for this consensus optimization problem is just storing and update a local estimate x sub I of the optimal solution theta star of the problem, okay? The assumptions that are here are the usual standard assumption in this kind of algorithm, where each cost function has a Lipschitz continuous gradient, and the summation of all the f sub I is strongly convex. Okay, standard assumptions. Okay. Then, what is the objective? The objective of this algorithm is to devise a discrete time update law, okay, for my local estimate, such that each of the x sub I converges to the optimum, okay? But not only that, so convergence is not our only objective, but we also want, as I already explained it before, we want to provide the stability analysis of the equilibrium. We want to show that you have maybe some ISS input to state stability, robustness property against disturbance, quantization, delays, and so on, okay? And what we proposed here to solve the problem that you have seen before is to do some feedback control integral action over a network. Because if you have this bias, for example, in this case, the first idea you have, okay, if I have a bias and I want to regulate and keep away the bias, then you add in integration, right? That is what we do in standard control, probably in first year control in undergraduate courses, okay? Okay, there is an enormous literature, okay, that deals with this kind of algorithms, but is all or most of all are in continuous time. Okay, let me then go a little bit into the details, okay? Let's start with the standard average consensus algorithm. So the standard algorithm, which is a gradient tracking algorithm basically, is just having this form, where you see that the local update in discrete time, x sub I plus, is the stored quantity x sub I plus a summation of the difference between x sub I, the local, and the x, which are the local estimate of the neighbors, okay? Where there are some assumptions about the adjacency matrix associated with the communication graph, which is the usual assumption that is written here, okay? It can be shown that the local solution converges to the average of the initial conditions, okay, with the assumption that the matrix K is symmetric and its spectrum is satisfying this condition. Okay, that is the standard literature result. Okay, but then how do you solve this problem then? How do you analyze it in order to get to the solution? Well, a naive decentralized gradient method algorithm is like this, where you add this red term here, okay, with a given arbitrary initially condition, and here you only know locally the cost function f sub I, and as again, you store and update a local estimate of the optimal solution, and you try to iterate to get to the optimal point. This algorithm does not work, as we have seen before. Okay, how can we make it work using control theory tools? Okay, the idea is quite obvious, let me say. So you add a control action. What is that meaning? Okay, so we take the previous form of the algorithm, which is written in black, and then we add a local control input. It's important that this is local, okay? That has to be computed locally on each agent. It's not a global thing. And we also add a disturbance, okay? A disturbance W sub I that in a way is also taking into account and allow us to factor in robustness analysis, okay? And we want to design this red element here, which is the local control action, such that we preserve consensus, of course, because this is the objective we want to achieve. We want to ensure asymptotic convergence toward the optimal solution. Important, this should be implementable in a decentralized way. That's very important. And we have to achieve robustness. These are our objectives, okay, when we design this U sub I against the W sub I. Am I going too fast or is it okay?
Oh,
It's okay.
the pace is fine.
Okay. Okay, now, how do we modify, how we design that? Well, we construct an integration linear feedback policy, okay? So basically here you see that then we create this integration system here, where also we include a possible disturbance here as well, okay? And you see that here the control action is then this consensus between the Z sub I, and the Z sub I are the one generated by this integral action that actually has the effect of filtering the consensus error, okay? Okay, when you plug that inside our algorithm, then something interesting shows up, okay? Because basically now you have these two iterations, X sub I plus and Z sub I plus, okay? This is the integral action that then is going to influence here, okay, the primary algorithm that we had before and that we want to robustify. Now, if you rewrite these equations for any I, so you write it in a compact form, okay, putting everything together, then the form of these two iterations is written here, which can be represented as a block scheme, like a feedback interconnection between this guy here and this guy here. And therefore, once you get that, then it is our comfort zone, right? For people that do control, this is the comfort zone. And we now can try to use the tools that we use in many of our control design problems, okay? So now what you can show, well, first of all, since this is a nonlinear system, clearly, what we can show first is that you need to understand which are the equilibria that are consensually optimal, okay? So then you introduce the set A star, which is the set of X and Z, such that you basically construct the stationary points, okay? So this set A star is containing all the stationary points. The issue with this is that when you try then to prove global input to state stability of the algorithm with respect to the perturbation W and Ni, okay, that has to be relative to this set A star, but this set A star is not compact. It's not compact, why? Because we want to achieve potentially global stability, and therefore it cannot be compact, and that is introducing some kind of technical issues when you try to prove the stability of that. What is the result we have achieved? And then I give just a sketch of the proof because some aspects of the proof are actually important. What we have achieved is the following result, okay, in a nutshell. Okay, we assume, as we did before, as we said before, that the communication graph is undirected and connected. And then we can show that every solution tuple of this form satisfies kind of an ISS condition like that, where here you see you have three terms. Okay, forget about the notations. This is not that important. But here you see that you have this term here, where mu is smaller than 1. Okay, and therefore this is a contracting term. Okay, and then you have two additional terms that depend on the disturbance W and nu. Okay. The important aspect to tell, however, and that is where the proof is actually based on, is the fact that these Wm and W perpendicular are the average and off-average components of this total disturbance, okay? And that is important because the way you prove this result is by a proper change of coordinates first. Clearly, if you take this relationship, and now we go to the proof, if you take this relationship, then when the disturbances are zero, then of course this theorem implies exponential convergence to the optimum, okay, with a convergence rate that you can write, and that is nice, okay? So because then this you get it for free, okay? Where this parameter C0 is related to the convexity parameter of the global cost. Okay, how do we prove this result? Well, as I said, I'm not going to every single details, but I would like to just explain to you that the key element here is this decomposition. So you see that here we basically redefine, we change coordinates, okay, where basically we consider the average and the dispersion decomposition of xz. Why average? Average because we want to have consensus. So the consensus is going to the average, right? And that is why that is one of the first component. And then we consider the kind of orthogonal component, let me say, which is the dispersion with respect to the average. If you do that, then actually when you rewrite your system in terms of these two new components, and you draw here the scheme that you have, then what happens is that you have a time scale separation. And that is very interesting because that is what happens in adaptive control, for example, where it is the time scale separation that actually enables you to analyze quite a lot of standard algorithms that define in adaptive control. The interesting thing here is that this time scale separation means that these two subsystems that are closed in feedback loop, okay, have a different rate of dynamics, basically, where the fast system is the consensus one, and the slow system is the average one, the optimization one, sorry. So this timescale separation is the one that actually does the job, okay? And here, this is written in a little bit more precise way. And the nice thing is that the first bullet point, the reason why the proof works is that after you do this decomposition, then the dynamic xim is decoupled, and it does not affect the time behavior of x and z. Therefore, you can neglect it in the proof, okay? So it doesn't affect, it's basically like being an unobservable element in this feedback interconnection. And therefore, that means that the slow loop, okay, the one that depends has this rate, okay, implies that for small gamma, irrespective of that you have disturbance, you get a stable loop. And that was what solved actually the problem of my friend, by the way. He then implemented that, and here you see that now, you see that the distributed algorithm that we have achieved by adding this integral action has always a convergence behavior for any set or any choice of the descent set small enough, of course, okay? And that was, I mean, we were even surprised a little bit about that, but that was an interesting byproduct of a very standard control approach to this distributed consensus optimization. And that we published that in a conference paper in CDC, okay? And we said, that's nice. Let's then work in this direction, okay? And try to address some more difficult problem, let me say, in optimization, okay? So here is basically the takeaways on this case one, okay? I think I said all these things already, okay? Maybe I would like to focus on the last two bullet points. The rest I already mentioned. First of all, the fact that we use standard control approaches means that what we do and the proof that we write are interpretable, okay? Because basically, the fact that we have the presence of an integral action in specific coordinates means that we have an integral control that is very well understood. And therefore, the algorithm itself is not just crossing fingers that it converges, but we have an easy interpretation, easy at least for us that work in control, okay? Second, the proofs are much simpler and shorter, and if you change the algorithm a little bit, you do not have to reinvent the wheel every time, starting from scratch, okay? And that, for us that we do research in this area, is also a nice byproduct of that. Okay, that was use case number 1. And of course, we were happy about that. Okay, let me now consider, in my opinion, a very interesting problem, okay, which is distributed global minimum sharing. Okay, let me first explain what this problem is in 4 different applications that are very different from each other, okay? And just to explain that this kind of global minimum sharing, distributed global minimum sharing, is actually something that could be applied in a number of interesting problems. So let me consider, and by the way, this is something that you guys that do a lot of things in transportation, of course, very well know, okay? So suppose that you have a very simple setup where you have a mixture of self-driving car, autonomous car, and human-driven cars, okay? Very simple scenario like the one that you have on the right, okay? And suppose that these self-driving cars are in a way used, okay, to kind of drive, how to say, the social dynamics of all these vehicles in such a way that you dump traffic ways or stop and go phenomena, okay? So you want to basically mitigate or possibly avoid these kind of behaviors. Okay, that is the scenario that we consider, okay? So therefore, no matter which control law self-driving cars will use, this is not relevant, eventually they have to agree on a common cruise speed, okay? And that common cruise speed is the maximum possible consistent with all the constraints. So each car has a different constraint, like this can be technological constraints, it can be traffic rules, of course, changing traffic conditions, the vehicle in front is slowed down, and so on and so forth. All things that you know. But then this problem means that eventually you have to compute in a decentralized way. That's very important. There is not a common supervisor of the traffic network. The problem boils down to compute in a decentralized way the minimum m star of all these local maxima, let me say, these maximal speed in this case that are unknown a priori to the others, right? So you don't know. One car could be a Toyota, one car could be a Ferrari. I mean, you don't know what the maximal speed is, okay? So basically, it's a completely decentralized problem. Okay. Second case. Suppose that you have drones, okay, and suppose which are agents, okay, and suppose that these agents need to elect one or more leaders in a decentralized way, again, okay? Typically, each of these agents knows a number, again, I call it m sub I to be consistent, which is unknown a priori to others. And for example, that can be a unique ID, a rank obtained in the pursuit of some task, and so on and so forth. And these swarms typically have a lot of variability, right? The rank can change continuously. The topology of communication change continuously, even in a stochastic way. So a common way, again, to elect a set of leaders in swarm is to choose the one having the least number m sub I. Again, this amount to compute in a decentralized way is m star. Third example. Testing problem, for example, in an infection network, okay, COVID-19 or a similar thing. And the problem you want to address is who is best to test first if you want to hinder contagion, okay? So suppose that you have an interaction network, for example, obtained from Bluetooth data or representing people's contacts and so on and so forth. Then with each node, you can associate a cost, let me say, that represent the societal damage if the person it represents gets infected. For example, this could be minus the page rank, okay? Again, the problem boils down to compute the same kind of minimum m star. Last but not least, because this is a practical problem that I'm working with, also with my company, okay, actuator synchronization in the industry, completely different framework. So for example, suppose that you have a number n of smart electrical actuators that you connect in series, and they need to agree on a common speed. Okay, in this picture on the right, you see, for example, the roller table of a flat rolling mill. Okay, so here you have, in this case, I think there are 130 electrical drives. Okay, this piece here is long 60 meters. Okay, just to give you an idea how big it is. Okay, and these drives, these electrical drives, of course, they have their own technological constraint. The load resistant torque is different from each other. And actually, if you have a solution where they automatically agree on the common speed, okay, then you enable automatic changeover, you enable adaptation to different loads and process setup, you enable plug and play replacement. So for industry, this is a holy grail, okay? And in fact, later on, I will show you also a simulation, some simulation result done for a real plant with a digital twin we have developed. Okay. So I think I provide enough motivation that this distributed minimum sharing is a problem that might be interesting, okay? And let me now go a bit more technical, okay? So here you have then n decision makers, the agents, okay? Each agent has a local number m sub I, as I said before, that is unknown a priori to the others, and the agents want to compute in an iterative way and in a decentralized way the optimum m star. What are our requirements, though? The objective of the research. Okay, robustness. Okay, robustness to changing environments. Okay, we want that. I mean, if for example, if the communication topology is changing at runtime, we want to be robust to that. And that, since we are control people, if you talk about robustness in a situation like this immediately calls for global asymptotic stability. Decentralization. The update laws only use local information, and the update law does not depend from centralized quantity. Scalability. The number of variables that each agent is storing does not depend on the size of the network and its topology. That is also an important requirement. And last but not least, uniformity. You want to have a convergence rate that is constant. It does not change. So if you change the initial conditions, you don't want to have a convergence rate that sometimes is seconds, sometimes is hours, okay? You want to have a uniform convergence rate. This is one of our objectives. Okay. So here, if you search the literature, there are basically two big categories of distributed minimum sharing algorithms. One which is called, I call it algorithmic approaches, and the other one is optimization-based approaches. Let me start with the first, okay? So let's take the more popular algorithm that is that you can find. That is really a fantastic algorithm, I have to say, okay? Because it's terribly simple and it looks very promising. It's the max consensus algorithm, okay? So here the algorithm is really, I don't want to call it stupid because it's not stupid, it's smart, okay? But it's very simple. So here each local agent stores a local estimate x sub I, and then the update, which means the update at the next time instant, is just taking the minimum of the local x sub j of the neighboring agents, okay? Just that, okay? It can be shown quite easily that if you initialize all the initial xi, okay, at the initial time, to the local m sub I, this algorithm does converge in finite time to the true optimum. And then one can say, okay, perfect. Okay, why should I bother to do something else? This seems to be working very fine. Actually, unfortunately, this algorithm and many similar algorithms have a significant drawback. Okay, consider our application-driven requirement that I showed in 2 slides ago. Okay, so suppose that at some time t sub 1, larger than the capital T where you had converged to m star, all the mi suddenly change to some value which is larger. Okay, suppose that this can happen. This can happen, right? A sudden change. That means that m star is now changing to a new m star. Okay, because all the local change go up, and then you have a new minimum. Well, it can be very easily shown that you don't track the change of the minimum. So it gets stuck where it was, okay? And the reason for that is that basically there is a non-observability situation, because in the first run, the max consensus does converge to a subset of the consensus manifold. But then, if the m star is going to change, this new value can be shown not to be observable, and then you get stuck there. And all the other algorithmic approaches, such fluid max, yaw, mega merger, and similar, have a very similar drawback, okay? Okay. Then we have the other category, optimization approaches, okay? What do I mean by optimization? Well, in that case, if you want to find that m star, okay, by an optimization tool, then you have to define a cost function, right? And here, for example, you can define a cost function like that, the maximum of a sum of these functions psi sub I that are continuous and strictly increasing, with the constraint that x sub I is smaller or equal than the capital M sub I, and xi is equal to xj for any I and j, okay? If you construct this constraint optimization problem, then m star is going to be the unique solution of this constraint problem. Okay, defining like that, in principle, is the solution to the problem. And now, how you solve this problem, this distributed optimization problem? Well, you can say, okay, let me take from the book, from the off-the-shelf tool, right? So the literature in distributed optimization is huge. And let's say, okay, let me pick some of the algorithms, let me try them out and see whether they satisfy this requirement here. Okay, this is our goal. Okay, so we want to find an algorithm, hopefully from an off-the-shelf one, okay, because I'm lazy. I just want to use something that works, okay? And then, however, I want to use something that works, but that is satisfied what I want to achieve, okay? All these properties, okay. Now, actually, none of the algorithms existing in the literature actually is able to meet all those objectives. And here I have a few examples, okay? So for example, if you take consensus-based subgradient second-order methods, they converge globally, nice, but you cannot, have constraints here. That's a problem. And the convergence rate is not uniform. Okay, dump it away. Primal-dual methods with inequality constraint. So here the constraint can be handled. However, they require a proper initialization, which basically kills the non-global convergence then, because it depends on the initial condition. Not good. Gradient tracking methods. Okay, here you have uniform convergence. However, again, you cannot put constraint in, and it requires initialization. Same problem as before. Probably the best category of methods are the ADMM ones, okay, very popular algorithm. So the node-based actually still suffers from non-global convergence. The edge-based one, which is probably the best, is uniform, has global convergence, but unfortunately is not scalable. In fact, every agent has to store and update a certain number of variables for every different connection with other agents. And that is a big problem for scalability and also for robustness, because what happens if the connection topology changes? You have to restart from scratch, okay? Which is also something you don't like. Okay, to sum up, okay, what is the scenario we have in front of us? Okay, we have two categories of tools, okay, algorithmic and optimization based, okay? We have found that none of them can obey all the objectives, okay? And also some optimization approach use centralized parameters that we don't like. And then the question we pose ourselves, can we have all properties? Yes, but, okay? So our answer is yes, we can, but provided that we compromise on exact convergence. When I say we compromise on exact convergence, I mean we have to accept that we can go close as we want to the exact minimum, but not exactly, okay? And we prove that, okay? So basically what we are going to show shortly is that our, again, control theory-based design yields approximate to an arbitrary precision with uniform and global convergence plus scalability plus stability. Or if you really want to go exactly at the minimum, then you have to give up something, okay? So in this case, we lose uniformity, unfortunately, okay? The blanket is short, basically, okay? And what we have discovered is that all the convergence analysis of this distributed global minimum sharing, actually, they don't look from a stability theory point of view, okay? And that is instead what we have done here when we design our algorithm. Okay, we need some assumptions, of course. We need a connectedness assumption. The communication network has to be I star connected, which basically means that every node is connected to at least one other node. Okay, that makes sense, of course. And consistency. Every agent has to know a lower bound for M star. Okay, at the first analysis, these assumptions seems to harm the decentralization, right? Because basically you say, oh, everybody has to know a lower bound, okay? Then M star is a global quantity, so what are you talking about? Actually, this is not a problem in practice because we can take a very small upper bound, and in practice, if you take the epsilon, that is the one that say how close you want to go to the M star, then you can just set mu sub I epsilon, this is the number that you choose, and then actually you do not need to have any knowledge about a non-decentralized quantity. Okay, how is the algorithm working? Okay, what is our algorithm? Okay, here is the algorithm. Okay, here I need to explain, of course, this equation because at the first look it doesn't look that it's understandable. Okay, let me first focus of what is inside the square bracket. Okay, the second term is the usual one. We have seen that already before, right? It's the usual consensus element. But then here we have this additional element here. And notice that this additional element here has an exponential term where this hi is positive. So this is an unstable element, okay? Which is the key point. And then outside here, okay, there is a projection operator, the standard projection operator, where you see that you project what is inside the square bracket between that lower bound that I mentioned before and the locals M sub I, okay? So at the end of the day, of course, this is not blowing up due to this unstable element because you do this projection. Clearly here, the key design element is to design this hi. This hi, of course, is a time-varying element, okay? And this is this is kind of an excitation signal or a dithering signal, okay? So the nice thing of the algorithm done like that, besides the theoretical properties that I'm going to show shortly, is that each agent can choose the gain ki independently to one another. And the same holds for the signal h sub I. So there is no need to coordinate those choices. So that means that you have a very good decentralization. You do not need to have any assumption of a column row stochastic matrix in your network, okay? And, which I think it's very interesting, only one variable is stored, okay? And that means that the scalability is very good, like the max consensus. So from that point of view, the algorithm has the same simplicity. Okay, let me then show what we can prove here, okay? Forget about this thing on the left, okay? Because it takes too long to explain. Focus on what is inside the green rectangle, okay? So here we have two options. when we choose H sub I, or we design H sub I. Either we have sufficiency of excitation, or we have uniformity of excitation. What is that meaning? First of all, let me see what is the consequence of that. If you design H sub I just to be sufficiently exciting, okay, then we show, and I give you the reference later, we show that you have exact convergence, but it's not uniform, okay? So the rate of convergence does depend on the initial condition. If you make the design of HI a bit better, and I will explain what that means. So if you design H sub I to be uniformly excited, then you have a stronger condition because you get uniformity, but you cannot exactly converge to zero. So let me first explain what is the difference between sufficiency of excitation and uniformity of excitation. So in qualitative terms, given any initial time t0, sufficiency of excitation implies that these signals HIT are positive frequently enough for a large enough amount of time after t0. If that condition does not depend on t0, then we have uniformity, okay, in the excitation. And actually, this seems very complicated if you look at that, okay? Let me just tell you, okay, just so how many slides I still have in front of me. So basically, we have that for every arbitrary precision epsilon, one can choose HI to guarantee that XIT converges to M star plus a ball of radius epsilon around M star globally for all agents. If, in addition, the sequence we choose is uniformly exciting, convergence is uniform. You know what is the easiest design of that, of HI that is uniformly exciting, is just a square wave. If you take a square wave, 0, 1, 0, 1, 0, 1, job done, okay? That works. And in fact, this is what we use in the simulations that I'm now showing you before I show you some more interesting experiments, okay? So here, let me explain what we have here. So this is an academic, okay, an academic simulation just to show what we have. Example number 1, we want to see whether there is robustness, okay, with uniform convergence, okay? So here we have 4 situations, you see from time 0 to 500, then 500 to 1500, and so on. So the first situation, we have 4 agents, okay? They have this kind of connection diagram. Then here are the local M's, and here is, of course, the minimum, okay? And we choose HI just to be a square wave, as I said before, okay? Then at time 500, you have 2 other agents that join, okay? So agents 5 and 6, you see that, of course, the topology is going to change, and the minimum is going to change as well. Then at time 1500, agents 2 and 3 leave, okay? And then in that case, the minimum is changing again. And then at time 3500, the minimum of M4 is changing, okay? So M4 was 13, and then now is becoming to be 8, okay? And then it's the minimum changes, and of course, also the topology is not the same you had at the beginning. Okay, now let me show what is happening here. Okay, here, remember that we have chosen H sub I to be uniformly exciting. So that means that we expect to have uniform convergence. And you see that you always track the minimum. Here you see different colors are the different agents, and M star is the dashed line here. And here with this zoom, you clearly see that you have a steady state error, right? So you don't get exactly to the minimum. However, the convergence rates is nearly the same everywhere, okay? So it converges with the same, let's say, time constant. How about max consensus? It fades, okay? Max consensus, of course, tracks the minimum until it gets to 7, but then when it gets up, it gets stuck to the minimum 7. It doesn't track it, okay? Then here we have a different example. Here I want to show you what is the difference in when you choose uniformly exciting sequence H or a sequence that is sufficiently exciting that then goes to 0 at some point, okay? So here you have the minimum that actually is changing in this way. The topology is constant. And here we want to just show in simulation how to say uniformity with respect to exactness, okay? And here, let me explain this figure here. So here you see that here you have the constant, the green one, okay? The green one is the one with uniform excitation, and you see that the convergence rate is always the same. But if you do the zoom here as before, you see that you have a residual error. Instead, if you have an HI which goes to 0 and it's sufficiently excited, then you converge exactly to the minimum. But you see that, for example, here, the convergence rate is much smaller than here, which is smaller than here. So you lost uniformity, okay? And max consensus fails again. Let me show these last simulation here. Here, let me tell, I don't know whether you hear the noise here, but this is a real plant. That is the roller table of the real plant. And this is the digital twin we have developed, okay? And here we want to use this global minimum sharing to do two things that both relate to actuator synchronization, okay? So one is to have the electrical drives on the roller table that are actually agreeing on a common speed, as I said before, but not only that, we also want to have the laminar cooling pumps, the shower that then cool down the strip, and I show you now what that means, also agree on a common cooling water flow rate, okay? We want them to self-organize, okay? We don't want to have a common control of that. We have developed a digital twin for that, with my company, okay? And we implemented in a real plant, which is located in the United States, in Kentucky, I think, okay? If I remember well. And it's in operation in the plant. And here, I'm going to show you what is the digital twin doing, okay? Here you have the rolling stand, and we are simulating the effect of the roller table with electrical drive and the cooling shower. Here you see the strip that is coming, and here you see the effect of the shower that actuates in an independent way. And here you see that what is the effect of the cooling on the colors refer to different temperature and so on and so forth. Okay, and now this is in operation, is implemented in the real plant. Okay. Okay, so to conclude this case 2, I don't think I have time for case 3, but anyway, let's finish the case 2. That is summing up what we have done. I think the main result from a scientific point of view is that the blanket is short and there is a need to compromise. There is no way to get away from that. But the interesting thing is that this selection of the HI is the key thing, and it's very simple to do. And this, for example, paves the way of doing an adaptive selection of HI. For example, this is something we start working on. But the interesting thing to me is that, again, wearing the hat of the control researcher, is that these dithering signal HI have a very nice analogy with what is done in extremum seeking, for example, with the dithering signal there, okay? Control towards set where observability is lost. Dithering allows to keep uniform observability. Take a completely different problem, least squares with the regularization. Again, the regularization can be seen as a dithering because it makes the problem well-conditioned. Or watermarking in cybersecurity, okay? Again, here you avoid replay attacks, and the watermarking can be interpreted as a dithering signal again. So what we have discovered is that these things that came up, you know, just because we find a solution in an algorithm, then it could have very nice interpretation in completely different problems, which was interesting to learn. I don't think I have time to go here, okay, and maybe another time, but I can give you the papers if you want, unless you want to have another 10 minutes, okay, and then I can finish. This is up to you. I think people are tired, but I can, just you decide. Otherwise, we stop
Uh,
here and I can give you the papers. It's not a problem. What is the boss saying?
I mean, we have 10 minutes, like we can definitely go over it.
Say it again.
Because, so, I mean, 10 minutes should be fine because people are going to look at it afterwards as well. They can
Okay.
do it once they
Okay. Anyway,
get
okay.
time
Then,
later. So we can.
okay. I will try to be quick. Okay. So this is the third use case, which is more complicated because now we want to analyze centralized constraint optimization first with the aim then to extend it to the distributed case. Why we want to do that? Well, if you consider constraint optimization, very standard constraint optimization, okay, a problem like that in the centralized case, we all know, if we know a little bit of optimization, we all know that this can be addressed by discrete time first order primal-dual algorithm, okay? Which in the discrete time, this is the Arrow-Hurwicz saddle point dynamics that can be written in this way. So this is a classical algorithm, okay, that is available in the literature for doing the constraint optimization. Basically, you are trying to get the Karosh-Kuhn-Tucker condition that everybody knows. Okay, but there are a number of facts. So we discovered that only local results were available. Okay, and these can be found in books, okay, which means that in the discrete time case, it was a long-standing open problem. I actually had a nice conversation with Dimitri Bertsekas because I know him, okay, and this conversation was 2 years ago because he was also visiting our research center in Cyprus, and I was asking Dimitri, okay, maybe it's just us that we don't find the paper, right? But in your book, it's written that the proof is only local, okay, for stability of that. And no, he confirmed that as far as he knows, it's only local. And in fact, there was a non-local proof in the 1950s, I think, by Uzawa, but it was lately shown to be wrong, okay? There was a problem in the proof, okay? In continuous time, no problem at all. The continuous time version is simpler to analyze, and there are many proofs of global exponential stability, okay? But unfortunately, when you discretize the dynamics, since you have discontinuity at some point, the mere discretization does not work. And therefore, global stability in the discrete time case with constraint is impossible, okay? So the question we pose ourselves, okay, because of the fact that only local results were available, we asked, can we go beyond local stability property, again, using a control theory-based approach, okay? Actually, the answer was yes, after 2 years of work, I must admit, okay? And basically, and I'm going to show quickly that, under widely adopted regularity and convexity assumption, the usual one, we can prove that the minimizer is semi-globally Lyapunov stability and exponentially attractive, okay? Careful, semi-global, okay? Not global. And in fact, when we submitted that paper in the first version, okay, we just say that. And then, of course, one of the nasty reviewers said, oh, but provide a counterexample then when you say that it's non-global convergent. And actually we did, okay? If you just consider this very simple problem, so I think any graduate student can play with it quickly, okay? So if you try to minimize x squared, okay, subject to the constraint x squared smaller or equal than 1, then you set f of x s squared, g of x s squared minus 1, and then you can easily show that this primal-dual discrete time algorithm, if you fix any gamma positive like that, every solution with initial condition that satisfy this condition grows unbounded, okay? It's a counterexample, okay? That was then motivating us to improve our analysis, and actually the result we have found are the following. So we have two assumptions that are quite common in the literature, okay? So F should be smooth enough and strongly convex. The constraint G sub I have to be convex as well and smooth as well. And there is at least one X, okay, that solves the optimization problem, okay? So if you then take the set of points such that the indices such that you have the active constraints, okay, then this is the assumption we make, okay? And the other assumption is that the vectors of the gradient of the G sub I computed in this point X star are linearly independent, okay? These are the typical conditions that you need in order to make sure that there exists a Lagrange multiplier lambda star such that you satisfy the Karush-Tucker condition, okay? That is standard constraint optimization assumption. Okay, then our main result, again using quite standard tools in nonlinear analysis, is that if you write your algorithm in compact form like this, where capital L is the Lagrangian function, and you suppose that assumption 1 and 2 hold, then for every compact subset sigma 0 of initial condition, notice every compact, okay? Every means that we don't care about the initial condition. Compact, however, means is semi-global, okay? You cannot take the entire Rn, okay? But for any compact subset of Rn, of initial condition, there exists a gamma bar, and for every gamma between 0 and gamma bar, there exists a mu, again smaller than 1 and bigger than 0, such that every solution starting in the set sigma 0 satisfies this contraction property. And that result established the semi-global asymptotic exponential stability of the optimal equilibrium, okay? And by the way, algorithm star can be approximately interpreted as a kind of a nonlinear oscillator, okay? And the reason why, after quite effort by my two collaborators, actually we were able to get to this result is because, unlike what Uzawa was trying to do in his proof, where he was using a standard Lyapunov function like x squared plus y squared, just to explain, we use a non-quadratic Lyapunov function having a nonlinear cross term. And with that, we were actually able to get this result and actually solve this open problem. And actually, this is the reason why it was published quite quickly in mathematical programming. So we were kind of happy about this. Again, using standard for us, okay, analysis tools that we use in our everyday research work in control. And to close, after we published that, then what was the next step? Okay, we said, okay, let's go back, however, to the distributed case. Can we extend that to the distributed case? It took another year of work. And here I have to say that it was key to have an additional collaborator, my young postdoc, Xiaoxin Ren. And actually, we were able to extend it, okay? The answer is yes. Basically, we combine what you have seen in case 1, okay, for the unconstrained case, you remember the case 1 we have considered before, and the centralized result. Combining the two, the paper is rather long, and then we finish. It seemed to be, for us, correct, and it's submitted to mathematical programming again, and let's see what's going on, okay? And yes, okay, and that is, I run maybe quickly, but here, crossing fingers, of course, as I said, okay, that will be correct, okay, and not wrong. We'll see the reviews. And here are the references, okay, that you have for this talk, okay. There are 4 papers. The initial conference paper at CDC 2022, and then there is this Automatica paper for the uniform global minimum sharing, and then we have the published paper on the centralized case, that actually is in 2024, and this new paper that we are waiting for the reviews to see whether it's correct. So sorry for rushing a bit, but I hope I convey the message that in control theory, we really have a systems theory approach can actually be very useful in a number of fields. We were surprised that in optimization we can get results, but now there are more and more works going in this direction, and that is, I think, that is a very nice thing, especially because optimization now is used in machine learning, is using in especially the distributed one, and therefore we think that we could have an impact as control community also in these areas. And with that, I finished now, really.
Yeah, thank you, Dr. Parisini. Yeah, I think we actually had a meeting with Xiaoxing Ren right before this talk. She was giving a talk similar to Andreas, and our group
Okay.
attended the talk, and yeah,
Okay, cool.
yeah, I
Cool.
could
Okay.
draw some
Yeah,
similarities.
she's fantastic. She is really amazing. So yeah.
Yeah, and we have some questions on the stream. Like I would, if you have time, I can just we can just go with them.
Are they in the chat or do you?
No, they're in the YouTube stream, so I'll let you know all the questions. So the first question is about for case one, the robustness of a distributed gradient tracking algorithm for
Mhm.
strongly convex cost functions. You've discussed that. And if we consider time varying momentum based accelerated algorithms,
Uh-huh.
how can we analyze the performance of these kind of algorithms?
We didn't do that, but if I understand the question, the momentum is a first order filter, basically, right? So it's basically, if I remember well, the momentum is adding a, let's say, when you have your update, okay, the update is xt plus 1 equal to something depending on the xt, okay? But then you add kind of a filter, okay, with xt and xt minus 1, okay? Something like that, okay? At least this is the momentum that is used in machine learning, okay? And that, of course, helps because it's basically adding a pole, an eigenvalue in the negative half plane. And so we didn't do that, but I don't think you have change a lot the proof, right? So because basically when you design the control law here, I guess you could add another state, okay, that is actually implementing this one first order filter with a momentum. You need to add another state, but since this is adding a negative eigenvalue, I don't think that this is destroying the proof. Honestly, I think the proof will stay. We didn't do that, but once you write the system in this form, I think that adding, of course, you need to add a state for each of the agent, clearly, okay? And to express this first order filter, I think it should work. I haven't tried, so it's if somebody of your collaborators are trying that, then please let me know because it could be an interesting thing. I mean, here we just design an integrator, okay? But I think you can design even a more complicated, control law, and that's fine. Provided that you though that you preserve decentralization, okay? That is important, okay? So it should be local to the agent, in my opinion. Otherwise, the proof changed a lot. That's my initial reaction to the question.
Okay, thank you. And this is a question from Andreas, and the thing is, like, could you elaborate on the potential consequences when on consensus if there are any communication delays between the agents?
Okay. You mean, Andreas, you mean that there is a delay here? This is what you mean? Because I think the communication that the agent I needs is just the communication of this xj, right? So xj is the x of the neighboring agent. I guess this is what Andreas meant, right?
Yeah, I think so, because like before the communication is the communicated estimate is being uh, relayed or received by the other agent. What if there is a delay in the time steps?
Well, I think that delay can have a very bad effect here because clearly that we know the delay in feedback, right? So it's I think the delay can be critical here, and especially because we have an integrator, and with the delay, it can. I don't know. Okay, it's a very good question, and yeah, in that kind of application that we use that with my colleague, the delay was not really a problem. It was very small, so you could neglect it, and the sampling time was quite fast. Okay, because here we are not considering that what xi plus means in reality. So what is that, the fast sampling? Is there a sampling or not? Okay, but I suspect that the delay could be very bad. Okay, so it's because it's in feedback. So at least I guess it will. You then need to have a very small descent step. So when you consider this this gamma here, I suspect that with the delay, this gamma has to be chosen very small in order to have. That is my guess. But I agree, it's a very good question. I think delay could be detrimental here.
Yeah, thank you, Dr. Parisini. Like we have a number of questions. Like, would it be fine if I direct them to you, like on email or something? Or,
Please do so. Yeah.
yeah, and
Yeah,
once,
because now I have also to go.
yeah, yeah. So once you answer the questions, I will just post them on our website or the stream so they can view it at a later point.
Okay, that's fine.
Yeah, thank you so much for presenting
So
this topic.
thanks to you for the invitation, and I hope that at least somebody enjoyed the talk.
Yeah, definitely.
Okay. Okay.
Thank you.
Bye bye then.
All right, everyone. See you next week, and thank you. Bye bye.